Hello there viewers, my name is Nasali Catherine and I'm going to be taking you through my project, the graph-based large acoustic reasoning models for multi-patient target sound destruction and respiratory monitoring in resource-constrained wards. I will name it GLAM. Yes. Large acoustic models are trained on massive amounts of audio data to understand and process sound. They recognize speech, classify environmental sounds, or detect patterns in acoustic signals in our word. When it comes to target sound extraction, it means isolating specific sound, the breathing, from a noisy mixture in the word. When you come to multi-patient monitoring, it means simultaneously tracking the health from multiple data patients. Then the graphical neural networks will be used to capture complex dependencies between these entities. Just know they are a graph-structured deep learning model that represents data in nodes and edges. The nodes could be the patient's symptoms or signals, while the edges represent the relationships and similarities. Real-time respiratory monitoring is critical for early detection of respiratory distress, yet it remains a major challenge in our country. Our project will propose an intelligent, scalable solution by leveraging large acoustic models, target sound extraction, and graphical neural networks that can isolate, identify, and analyze multiple patient respiratory sounds at the same time. We shall use explainable AI techniques to ensure transparency of predictions, and knowledge distillation will be used to enable deployment on low-cost edge devices. These are the papers we reviewed. Starting with the waveformer, it proposes a transformer-based real-time target sound extraction capable of isolating sound from overlapping mixtures. It helps us build our transformer-based attention models for real-time patient separation. The limitation in this paper is that it was tested on synthetic and single-channel audio mixtures, which limits generalizability in the real world. When it comes to the second paper, it proposed a novel approach for environmental sound classification, representing audio data as graphs. So it used dynamic audio-generated graphs for scalable patient event modeling. The limitation with this was that the method relies manually on constructed graphs, and does not explore adaptive graph construction strategies that can be used in real life. The third paper proposed a deep advanced learning framework for classifying respiratory sounds by integrating multi-channel articulation signals with male frequency conceptual coefficients. So this paper used the deep learning approach for accurate pattern classification, and the limitation to this paper was that it was trained and evaluated on a limited data set, which was also imbalanced, which restricts generalizability in clinical environments. Now, lastly, we looked at a paper for knowledge distillation, which provides a comprehensive overview of the evolving field in knowledge distillation, basically enabling lightweight deployment without losing interpretability and accuracy. In Uganda, there is a critical shortage of scalable respiratory monitoring technology, and it can be divided into two problems. We have the domain, where we have limited medical equipment, high equipment costs. If the equipment is existing, it doesn't monitor multiple patients, and the medical personnel is limited. When it comes to the computational problem of the equipment that is already existing, we realize that the source separation is not good because they use traditional methods like ICA. Then we have feature extraction is limited. For example, when it comes to people who have similar breathing frequencies, the models sometimes get confused. They don't have graph-based reasoning, and they are resource constrained. Yes. These are the research questions that we thought about. I'm just going to let you pause the video so that you can read through them. They are precise Okay, so we use two datasets, both from the International Conference on Biomedical Health Informatics 2017 Challenge. The one from Hugging Face was recorded using the oscilloscope, and its distribution, as you can see, is here, given in this table. It's as simple as you see it. Yes. Then when it comes to the official website, it had much complex data. These had different scenarios. There was multi-channel and single-channel recordings from different locations on the body. There was a mouth, a microphone for recording the sound as well. Then from these different postures, they came up with a dataset that had 5 hours of recording from 126 subjects. Yes. After doing an EDF for the first dataset, I realized that the distribution, the most important things to get out of this is that the duration for the audios is 20 seconds plus or minus 3. Then you would say that the COPD was the most represented class with the no potential defects detected. This is the healthy class. But when you look at this graph, you realize that there are classes like the asthma and the LRTI that are underrepresented. And this happens in the second dataset as well. When you come here, you realize that we had different recording equipments. This is the EDF4 dataset 2. COPD is the most represented class, and it was recorded using different equipments from different chest locations. The arterial right, arterial left, the pulmonary left, pulmonary right, as you can see here. And when you check out these other graphs, you realize that the chest locations had minor representations for these other classes, with COPD having the biggest percentage of data. It's going to be hard to classify other classes when it comes to model training. Here is the first breakdown of our architecture. It has 9 layers, starting with the data collection, where we shall have the multiple audio streams being taken to the preprocessing layer. We shall remove the noise, the band and band pass. Then later on, it will be taken to the source separation layer, where we shall have multiple source separators. Then these isolated audio streams will be taken for feature extraction. Then we shall have the melospectrograms, the MFCCs, and the breathing detection, plus the respiratory rate and the advantageous sounds. From these sounds, which have been separated, we shall now tally them with the patient's attributes. Yes, the audio streams will be matched to the beds and where these people are. Then we shall do the reasoning and analysis, where we shall have the graph construction, the events, and the temporal windows taken care of. With this, we shall proceed to the relational reasoning and the baseline modeling for the individual patients. From this, we shall take it to the anomaly detection. Remember, it's collecting data from the patients. Now we shall have rule-based thresholds and patterns deviations made for each patient. Then we shall have a machine learning based detection used to get the anomalies. Now from this, we shall deploy this model that has both the reasoning, the attribute layer, and the anomaly detection, then deploy it. With this deployment will be distilled. And with this deployed model, we shall have an alert and interface layer that will generate alerts showing the patient ID location and the severity of this alert. Yes. So these are the three models. We have the YAMNet. It's a large acoustic model that is already pre-trained. It uses ensemble classifiers, and the innovation in our pipeline is the feature engineering. It's a classifier by default, uses basic weighting, and we used 3 of them, 3 classifiers, so it chose the best out of the 3, and this was what it used to produce the results from the testing. When it comes to the GLAM version 1, It uses multimodal fusion, whereby it has a large acoustic model, a graph attention based model, and creates a we created a multi-patient relationships and scenarios while training this model. It uses cross entropy for the loss function and Adam weights to prevent Adam weights with early stopping to prevent over overfitting. For the GLAM version 3, it learns from scratch. It's a PyTorch deep learning model that uses spectral patterns and end-to-end learning. It's a simple CNN. It has balance optimization and it has advanced imbalance handling.
This is the performance of the models. So for the YAMNet, we got the dataset and placed it in three categories: COPD, the healthy people, and then the guys who are suffering from other respiratory diseases. Now, the performance is actually good. It's above 80, which is a good thing. Our model has a higher chance of prevailing once deployed, but when it comes to the GLAM version 1, it faced a severe case of overfitting, and you realize that the COPD performance is great, but when it comes to the rare class performance, it's actually very poor. You see, out of the 28 samples, we had 3 classes, but only the COPD class had the best results. Now, when it comes to the GLAM version 3, what we do is we get this dataset, then we allow it to learn the features from scratch of the COPD patients and asthma patients with other patients. So these features are stored and set as bookmarks for this model to learn. Now, the rare class performance is actually good because since the classes are going to be used as benchmarks, they will be stored and kept as reference. And COPD, this performance kept on increasing, thus giving us a validation accuracy of 80.29%.
These heat maps are just a representation of the things that I have already discussed about the models. And as you can see in these images, you can realize that COPD across these models was the most classified or the best classified amongst the rest. So moving forward, right now the models can identify a COPD patient from a healthy person. But when it comes to the other classes, that's where the issue comes in. So more work will have to be done in that aspect. Now, the limitations we faced while working with the data sets is that there is severe class imbalance. Augmenting the data creates fake samples which don't exist in the real world, which means deploying the model it might underperform. And the scarcity of the data sets of patients in the classes that were underrepresented also is a big problem because they are not in a ward setting, like in a multi-patient environment. Moving forward, we want to look to fix the imbalance by using class-aware sampling or curriculum learning. This model has been trained on a dataset that has many respiratory diseases, so it will use that as a basis to build up more information about those classes. We want to use a multitask or semi-supervised learning that will allow the model to predict multiple things at a go. For example, the disease class, the severity score, the audio quality, or even the background noise levels. We want to use a federated learning loop, the one that we talked about before, that will work for post-deployment. Now, multi-patient scenarios will be used when testing the models so that we can be able to know if they are working or not. I would like to thank Mr. Galiwango Marvin, our supervisor, for guiding us in this work. That's it from me. See you next time.